Okay, so good evening, everybody. Uh, I am Moina Ghoshal. I am a PMRF at ISAR Kolkata, and I have been taking this session, which is regarding assignment of week number 7. And this course was named as application of spectroscopic methods in molecular structure determination, which was taught by Professor S. Shankara Raman. And I am the TA for this course. And in the previous 6 modules, I have what I have explained in the first 3 modules. I have explained about NMR spectrum. I have solved some problems regarding NMR spectrum. In the next 2 modules, I have solved some problems regarding mass spectrum. And also in the very last module, I have discussed about this IR spectrum and also solved some problems regarding the IR spectrum, and which will be helpful for you to utilize this data, these sets of data, to actually analyze what kind of compound you have. Okay, so if you want to make sure that what compound you think is made, then you have to match all the data that you have got through spectroscopy. That's why this course is very much important. And today, what I will do, I will not talk about any kind of spectroscopy. Rather, I will do a mixture of all the spectroscopic techniques that you have learned so far. That is mass, carbon 13, proton NMR, carbon 13 NMR, proton NMR, and IR spectroscopy. So these all techniques will be used by you. These techniques will be helpful for you, and using these techniques you need to solve some problems which I will show you, and you have to predict what kind of structure does the molecule have, right? So let's start today's session by solving problems. So this is the first question that I am going to solve today. You have to deduce the structure of the organic compound using the data given here, given spectroscopic data consisting of IR, mass, 1H, and 13 CNMRs and UV. Okay. So for now aspect, I have some questions today, among in which UV is also given. So you don't need to worry about UV. UV I will discuss in the next session when I will talk about UV, and all the things will be then clear. But other than UV, without using UV, how much or how far you can proceed, you first try to do that. Okay. Then UV will what information you will get from UV today I will just tell you, and you will then discuss it in a broad format in the next module or next assignment session. So for now you have seen that IR data is given here. You have the mass data, and the molecular formula is given in the mass. Molecular formula is given C9H11NO2. So from here, just a minute. Just a minute. Okay, sorry for the interruption. Okay, so you are given this data, and the molecular formula is given right here, which is written as C9H11NO2. Okay, so from here you have given IR spectra, you are given mass spectra and fragments are given. Also in the next slide, I have given this NMR data, which is not clearly visible, but I will explain to you all. And also you are given this proton decoupled and proton of resonance decoupled third order carbon spectra. So from here, you need to predict what kind of molecule is possible. Okay. Okay. So first of all, you need to find what is the double bond equivalence of this compound. C9H11NO2. So double bond equivalence or DBE, it should be 9 minus 11 upon 2 plus 1 by 2 for nitrogen plus 1. So this will be 10, 5, 6, 5, 5. If I am not wrong, this is 5. 9, 1, 10, 5. Okay. So double bond equivalence is nothing but 5. Okay. So if you see there is a double bond equivalence of more than 3 or more than 3 or 4, you can expect a aromatic compound. Okay, can expect, but this may be possible, it may not be possible, but you can expect that. Now you need to see the IR spectrum. Okay, here you see the IR spectrum, a band of signature band of 1670 centimeter inverse is observed. Okay, so in IR, is the IR spectrum. One peak is observed at 1670 cm inverse, right? Another peak you can see it's almost 2900 cm inverse. Also, a double peak, that means what I am talking about, this peak is over, this is I have taken, and there is this one. Okay, this is almost 34,000 to 36,000. Okay, so double peak. So from IR, I can get that three things are there. Okay, first of all, there is a peak at 1670 cm inverse, 2900 centimeter inverse, 3400 to 3600 centimeter inverse. Okay, I should take a new slide, that will be very helpful for you. Okay. So, question 1. In IR, whatever you have got a peak at 1670 cm inverse, one at 2900 cm inverse. Another thing you have got that you have 3400 to 3600 cm inverse. So what kind of functional groups could be present for which this IR spectra could be seen? For this 1670 centimeter inverse, what kind of group could be present?
Sir, ester.
Carbon.
Sorry,
Sir, ester, maybe ester.
maybe ester.
Yes.
Okay, I mean there means carbonyl, right?
Yes, sir.
Yes. Anything else?
Sir, alkene.
Alkene comes below or nearly 16,000. So it's above I mean more than 16,000. So
Possibly an amide.
amide means amide is a huge group. Two functional groups are there. Which one you were talking about? CO or NH2?
CONH2, yeah.
No, I mean We were talking about CO and NH2, two groups are there, CO and NH2. Which one is corresponds to 1670?
1670 is for the carbonyl and NH2 is because it's single, two peaks are coming, so it could be an amine, primary type.
Primitive amide. Okay. Anything else? Okay. Someone is saying this is ester, like this one. So, this 34,000 to 36,000, you can see here two peaks are there. So, which actually corresponds that which is very much possible that NH2 kind of group or secondary, primary amine kind of group is present in the molecule. This is very high chance. So, primary amine. Okay. So, what is for this one? This one actually corresponds to which one? sp2 carbon hydrogen or sp3 carbon hydrogen, this type of functional groups comes in this region. Okay. Now you have got that you have some ester or amide kind of thing, and also you have any primary amine. Okay, so one thing is confirmed that your NH2 is present in the molecule, and also C double bond kind of functionality is also present in your molecule. That much information you have got. Okay. Now, among which ester or amide would be present, what is the possibility that which one will have higher possibility to be present? So you can see here that the amide for the here in NMR there is exchange with D2O kind of peak and a broad peak, which is only possible if NH2 group is present. For amide, it is very difficult to exchange proton with the compound, with the solvent. Okay, so NH2 group is actually confirmed that it is not present as an amide, it is present as isolated NH2. Okay, so the possibility is that it is nothing but some kind of ester, because it is not carbonyl, because carbonyl will be more than 700, 1700. So there is a possibility that ester kind of thing is present. We cannot confirm that ester is present, but there is a possibility that ester is present. Now, coming here, so I have not talked about UV that much. So this transition up to now, you just remember that this transition at 230 or 240, this corresponds to a aromatic ring. Okay, so this is an indication of an aromatic ring is present in the molecule. Okay, then you will also get another too much evidences for the presence of this aromatic ring when you will count the number of signals. So one thing is there that you have some aromatic ring. So what is the possibility? You have some aromatic ring, you have some NH2, you have some C double bond O kind of thing, and what else? sp2 carbon hydrogen. So aromatic ring, you understand that there is a very possibility of sp2 carbon hydrogen presence. So IR can give this much of information about the compound. Now I am going to another spectroscopy technique to get more information. In mass, I can see a peak at 165, and I am writing all the peaks 137, 120, and 92. So mass spectrum. Now I am analyzing mass spectrum. Okay. So in mass, molecular ion peak is nothing but at where it is 165. Yeah. Now we get fragments uh, 137, 120, and 92. Right? 137, 120, and 192. So you first need to know that how much amount of mass could be lost so that you can get a fragment of 137. You can easily calculate. It could be a possibility that a mass loss of 137 to this one is 28, nothing but 28. Okay. Okay. From there is a possibility that 17 unit of mass loss could be possible here, and from there 92, that means from here to here there is another loss of 28. Okay, so this is nothing, the whatever I have written in parentheses, this is nothing but the loss in mass unit. So you need to find which fragment could be possible that this mass is lost from the compound. Okay, but this does not give us any information regarding the structure of the compound or what kind of compound could be present, but it gives some idea that what kind of fragments could be possible in this compound. And the loss of 28 maybe loss of 28 is due to CO, carbon monoxide or CO. Okay, this is have a mass of 28. This is possibility that 28 mass loss could be due to this compound, this CO. So IR and mass is not able to give me any information about the structure of the compound, and neither it is possible using the UV visible spectroscopy. Okay, so we need to go to another spectroscopy techniques to get some information about the compound. Now we go to NMR. In NMR, you see an interesting feature that the water solvent exchangeable proton is there, which clearly indicates that an isolated NH2 group is present in the molecule. Okay. Now you see in this region, which is also known as aromatic region, you see a AB quartet kind of thing. Okay.
Can I have a clearance of doubt? How do you say it is an isolated NH2 from the proton and number?
Because if NH2 is attached to any kind of group, if it is nitrogen is going to resonance, it is very difficult for this to exchange proton with the solvent. That was I have told you that if it is attached to any kind of group, it is very difficult to remove the proton from this NH2. So that's why exchangeable proton, that means it is an isolated NH2 group. Got it?
I'm not clear.
Okay.
No, I understand that any exchangeable proton, either in NH2 or an SH or OH, will have a deuterium exchange.
Again.
You can easily identify the presence of the protons, particularly in a OH or NH or SH. You can do a deuterium exchange.
Yes. But always all NH will not give the same thing, right? You see here, this is an amine, this is an amide. Okay. So this proton is acceptable by both, is in the equal amount. Here, nitrogen has a chance of resonance, right? Right? Very much difference is that it is very difficult for it to exchange proton with the solvent. But if it is attached like this, isolated means it is not attached to any kind of other functional group for which the nitrogen can undergo conjugation. That is what I am saying. Now you got it?
Okay. In between, I got disconnected. Or you can hear. Okay. No problem.
Have you heard?
Please go ahead.
Okay, so you got your answer, right?
Sorry if you could repeat it again because I got disconnected.
That's what I'm asking. Okay. So for you see here, one is amine, another is amide.
Yeah, fine.
Fine. So if nitrogen lone pair is involved with the conjugation of this carbonyl, so this availability of this hydrogen, will it be same with this hydrogen?
Will be different.
Different, right?
Yeah.
So that's what I am saying that isolated NH2 that means it is not attached to any kind of functional group, or like this one, and nitrogen lone pair is not involved with conjugation. Have you got it?
Yeah, got it.
So this actually gives us idea that what kind of functional group is present, and here one thing is that the isolated NH2 is present in the molecule. Now one thing you see, Here you see how AB quartet kind of pattern, right? So this AB quartet actually indicates clearly that this kind of pattern is very possible. Para disubstituted aromatic compound. So you have seen in the previous assignments also that if there is a chance of AB quartet, if you in any kind of signal you see AB quartet kind of thing, you can identify that there could be a possibility that it is a para disubstituted compound. Okay. Now what could be the substitutions? Okay. So one substitution, one group, I can identify that it is isolated NH2 group. So one group is NH2. Okay. Now you see other patterns. So here you see, if you can, I don't know whether you can see it clearly, but I should write it. Then you will be able to understand the delta. Here is 4.1 or 4.2 quartet, and there is another delta. That means this one and this one. This is nothing but 1.3 kind of thing. This is triplet. And you see the hydrogen, if you count the number of hydrogens, and if from there you can say that 4.2 quartet and 1.3 triplet, what could be possible? What kind of group is possible from here?
Ethyl group.
Ethyl group, exactly. Ethyl group. Only ethyl?
An oxygen connected to CH2 is making it highly deshielding to 4.2.
Exactly. That's all. That's what I want to say. Yeah. So that normal CH2 will not come at 4.2, that will come nearly 1.5, 1.6, I think. So if it is connected to oxygen, it is highly possible. I have shown you in the previous assignments also, that ethoxy group would be present. Okay. Now, so you got another ethoxy group, and in the previous case, you have seen some ester kind of functional thing which could be present. Now you count what could be the number of, what would the molecular formula. 1, 2, if you see this, I am just counting 1, 2, 3 carbon, 6 carbon in aromatic ring, so C9. Here 3 to 5, 6, 7, 8, 9 to 11, 11 hydrogen, 2 oxygens, one for carbonyl, another for this oxygen, this is this ester linkage, O2, and 1 nitrogen. So you see, this is the formula that I have told you, that C9H11NO2. So you have arrived at the formula. So the possibility is that it is like this. Now I need to verify this compound with other mass spectroscopy techniques and also 13 carbon, that whether this structure what I have predicted is possible or not. So I'm writing it the structure here. Okay, so it has a molecular mass of 165, that is given in the mass spectrum. If you calculate, you will get 165. Now from here, what kind of fragmentation is possible? Most important fragmentation that is possible of this one. Okay, this one is highly possible. Now you see that before, so how much of mass will lost if this group gone? So you will lost OET group, right? So you will lost OET group. So if you count the mass, oxygen is 16, CH2 is nothing but 14, so 14, 16, 30. This one is 15, 45. So if you lost from 45 from 165, you will get, yes, 120. And you see one peak is there at 120, right? So the 120 peak is nothing but this one. So if oxygen lone pair will be there, so plus charge. This one. I should draw the structure properly. So one mass peak that is present in the molecule is matched here. So this peak is at m by z of 120. Okay. Now you know that from this compound you have seen you will go up to here. You have went up to here. Okay, 120. From here you see a mass loss of 28. And you know what I have told you, that there could be a possibility of loss of CO. And you see from here CO loss is very easy. Okay. So you will left with this one. Okay, this NH2 kind of thing. So if you count what will be the mass, you will get 92. Okay. So two peaks you have already assigned. Then what could be the possible two peaks? Now you need to assign that what is the reason for this one. So these two you have got, that what kind of functional groups could be lost and what kind of fragment could be produced. But what is a possibility that it will get a peak at 137? Here, from here, this loss of CO is not possible. You can see here. So what could be the possibility? So there is a possibility so initially when a molecule will be radiated, there will be a high chance that when the molecule is radiated, you know that to get the peak here, there a cation radical will be formed always. So from there, suppose I am writing like this compound. Okay. So cation radical will always be generated. Now from here you see, if this oxygen takes this one, it will give this one and this will release. Okay. So what is releases? It releases a molecule of ethylene. You can see here. So if okay, like this, or maybe you can see it in the homolytical cleavage. Okay. So then you will see have this radical kind of thing. So now you see, so from this one I write it here. Yeah. So I just arrange this. Okay. So it will form like this one. Okay. So positive and radical will be separated between these two, right? So if you see here that how much mass is lost, you have lost a molecule of ethylene. And how much is ethylene? Ethylene is 28. Okay. So there is this compound is possible to form. So if you want to refer it as how mechanism is happening, you can refer to this Pavia book also. There the separation of this molecule in case of ester, how this is forming this kind of acid kind of pattern is clearly illustrated. Okay. So all the peaks I have assigned in this compound. Now I need to check that carbon 13 NMR, which is left only, is this matching with the compound or not? So here the compound is written over here. So how many different carbons are present in the molecule? How many different carbon? How many different carbons are present in this molecule?
Sir, 7.
7. Okay. So 1, these two are equivalent. 3, these two are equivalent. 4, 5, 6, 7. So in the carbon spectrum, you expect 7 peaks to be present, 7 distinct peaks to be present to confirm that the molecule whichever you are thinking of is correct or not. So see here, how many peaks are there? You just count it. 1, 2, 3, 4, 5, 6, 7. You should not take this one, okay? 77 peak is nothing but CDCl3 peak. So 7 peaks are there, it is correct. Now you need to assign which kind of peaks is which one. So peaks at 169, you can see a peak at 169. You can see a peak at 141, right? Or one, sorry, one, but it is 151. You can see a peak at 130. You can see a peak at 119 or 120. You can see a peak at 115. Nearly this one. You can see a peak at 60. You can see a peak at 15 kind of thing. So 7 peaks you can see. Now you need to assign for which carbon which peaks will be possible. So this 169 peak is for which carbon? I have named it 1 to 7. So can you tell me which for which this 169 peak is there?
Sir, for 5.
5, right? Right. Carbonyl carbon will be highly decelerated. 5 will be 169 one. Now 151 one. Which one will be 151? This carbon is highly decelerated because of highly electronegative oxygen. So next carbon will be that one which has less electronegativity than oxygen, right? So among them, it's nitrogen is possible. And it is attached to a carbon which is carbon number 1. So this carbon number 1 will have 151 kind of peak in the NMR 13 carbon NMR spectrum. So this 151 actually comes from this one, right? So other two, 130 and 119, you can easily guess which one is which one.
2, sir.
2 is 130, right?
3, sir.
Next one is 3.
Yes.
Next one is, which one will be higher? This one or this one? 3 or 4? Actually, 4 is attached to this carbonyl oxygen, carbon, right?
Yes, sir.
It will be much a bit more decelerated compared to 3. So it will come, they will come very close. This is 119, 112. You can easily see. So it will come a more decelerated compared to this one. Okay. Now you see these two are left only 6 and 7. So 6 is only 61 and 7 one is 15. So you have assigned all the spectrum for all the groups or all the things that you need to confirm that what compound you are predicting is correct. So you have matched it with the NMR spectrum, you have matched it with the mass spectrum, and also you have matched it with the IR spectrum. So this is the compound that we are talking about. Okay. 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 Now going to the next question. Picture is little bit of blurry kind of thing. So I will dictate that for you. So you need to reduce the structure again from the data, but here not UV data is not given. So the follicular formula is given C12H14O4. So you see here one peak is there, a peak at 1725. If you clearly see, I write it 1725 and 1300 live thing. Okay. In mass, this peak is 222. This peak is 177. This is 145. And you are given the molecular formula I have written over here. This is C12H14O4. Okay. Now I am going to the NMR spectrum. This is very messy because of this bloodiness. So first of all, again we go one by one and we will solve the problem. First, you need to find what is the double bond equivalence. See, 12 minus 14 by 2 plus 1, 7, 6. There is a high possibility of a aromatic kind of thing would be present. Right now, the peak in the IR you see first at 1725 cm inverse. You see a peak at 1300, right? At 300 there is a peak. Yes, Rasid? Yes, Rasid. Go on. Yes, Rasid, you want to tell something? Anyway, okay. Now I'm going to the point that a peak is observed as 1725 centimeter inverse, 1300 and another at 3000. So what is possibility that 1725 centimeter inverse peak is possible? Which functional group could be present?
Carbonyl.
Carbonyl. Okay. Yeah, you first predict carbonyl, whether it will be ester or normal carbonyl or aldehyde or ketone, that will see later. What could be possibility? Okay, 1300 is the fingerprint region. I am not bothered about that many more. So 3000 will be which for which one is 3000 peak? In the previous question also you have seen a 3000 kind of thing. This could be due to sp2 carbon hydrogen. sp2 carbon hydrogen. This 3000 peak could be possible. Okay. So this carbonyl and sp2 carbon hydrogen is present in the molecule, right? Now you see the mass spectrum. This 222 kind of thing is there. So mass spectrum. So 222 kind of thing could be there, molecular ion. So here, if you lose next fragment, one fragment is at 177. So how much is lost here? 23 and 22, 45. Okay. Another fragment it has 145. So how much is lost from here? You can see 73, 7 and 45. How much? 22. Right. So from here, two peaks could be possible. So this is 149. Okay, sorry, not 45. This is 149. So then how much it will be? 8. Yeah, 28. Yes, now it is okay. So in the previous case, you have seen that 45 mass loss could be due to presence of OET group, right? Could be presence of OET group. If you see this OET group will left, how much it will left? 45. And you have also seen that after the leave of OET, the carbonyl will remain as this one, right? And hence this will be readily lost, and this will lose a mass loss of 28 unit, right? Carbon and oxygen. So here you can see there is a mass loss of 45 initially, followed by a mass loss of 28 in the next stage, which clearly indicates that there is a possibility of this group present. Okay. And also in the IR spectrum, you have seen that carbonyl functionality could be present. So this group is only present in the molecule, right? Now, so one group you have identified, this is CO2 ET. So any more information from here? No, we don't get any much information from here. Now I am going to NMR. Okay. So here you see one thing. This is what is this one? Delta 4.1. Again 4.1. This is quartet. This is 1:3:3:1 pattern. And here you see this is triplet. Delta of 1.2 or 1.3. This is triplet. So since in the previous question you have seen that the presence of 4.1 quartet and 1.3 triplet, this is an indication of presence of OET group. So you have confirmed that OET group is present in the molecule, right? Now you see here that what is this pattern? You cannot see, I think, properly. This is doublet of doublet of doublet. Okay, this is a doublet of doublet. This is another doublet of doublet. Okay, so two doublet of doublets could be there, or here you will see this is a multiplet pattern. Okay, so considering this as a multiplet, so I have something, and also I have some peaks in the ring in the range 7 to 8, which clearly indicate that aromatic region. Okay, in the aromatic region. Now, so I have some aromatic compound, CO2 ET group. This much information I have obtained till now. So what I am left with? If I can remember, what is the formula? C12H14O4. C12H14O4. Right? Now, you just count it. This is nothing but C6. Suppose CO2 it is attached to this one. So one hydrogen is lost. H5 kind of thing. Suppose. So CO2 ET and C6H5. Count it. C7. ET means CH2. Sorry, C7 not C7. CH2 CH3. Yeah. C6, 7, 8, 9. Okay. So C9, H5, 2, 7, 3, 10. Right? C9, H10, O2. This is the pattern. This is the group you have already obtained. So what are you left with? So you see in NMR you don't see any other kind of pattern rather than, so for aromatic proton you will get some pattern, right? And for ethyl group you have got some pattern, and you have got no other patterns, right? That means you need to find out what is left you are left with. So if you just subtract it, you are left with C3H4, right? H4O2. Okay. Yeah. So what could be the possibility? C3H4O2. So now, since you have seen in the spectra, no other group is present, and in aromatic ring, you see a doublet of doublet, two doublet of doublets, which clearly gives you a multiplet kind of thing. You can easily predict that only CO2-ET functional group is present in the molecule, and you have not seen also any kind of functional group presence in the IR spectrum also. So there is a very high chance that CO2-ET group is only the group present in the molecule. So the remaining part which is left, it is nothing but CO2-ET. Because in the NMR I have seen no other signals for another hydrogens or another protons. Okay, so there is a high chance that there is a CO2-ET. Does this match with this formula C3H5O2? But here is H4O2, so one if another CO2-ET is possible here, so one hydrogen will be lost, so you'll feel CO2-ET. So you will left with CH5, H4, because two substitutions, two CO2-ET groups will be present. So the structure, so I will take the new slide. So what do you have right now? This CO2-ET, one is CO2-ET. Another is another CO2-ET, which you don't know where it is positioned. It could be ortho, could be meta, could be para, right? But one thing I should clear you that it could not be para. Why it could not be para? Okay, three kind of structures could be possible. I am writing one by one. This is one structure that it is para. So it could be meta. It could be ortho, right? Okay, so it could be para, it could be meta, it could be ortho. Which of these following is the structure of the compound? You can easily tell from this idea of your NMR spectrum. Which one will be the correct structure? If you see
Sir,
anyone,
ortho one.
why ortho one?
Because sir, if it was para substituted, then we would have a AB quartet type of thing. But
Correct.
here we have a multiplet.
Yes.
And if it is meta, then we would have one hydrogen singlet.
Exactly. That's what the answer I wanted.
Yes, sir.
Exactly. Very good. Yeah. For this hydrogen, you will expect singlet, but you have seen no singlet. You have seen only multiplets or doublet of doublets here. So these hydrogens will actually come as multiplets. Okay, this will be our doublet. Again, we will metacoupling will doublet. So you will see a large number of pattern and no singlet kind of thing. So only possibility is that this is nothing but ortho substituent. So I am just removing all these other possibilities. Now I am writing this structure. So I am writing this one, C double bond OET. C double bond OET. Okay. So this is the possible structure. Now I need to verify it with the mass and with the carbon 13 NMR data. Okay. So in mass you have seen, mass you have already checked, right? I have proved from mass that OET group is present. Okay, so one thing is already done. Now another thing is that you need to verify your carbon 13 data. So how many in this ortho compound, how many different number of carbons will be present?
Sir, the 1,4 disubstitution is the most possible, na, sir?
If 1,4 disubstitution, that means the para 1 could be possible, then you should expect the AB quartet kind of pattern.
Yes, na, sir.
Here you can see AB quartet.
Double bond. Okay, okay.
No, in NMR spectra, you are seeing AB quartet. This is not AB quartet. This is AB quartet kind of thing. See, this is AB quartet.
Yes, sir.
Right?
Yes.
Yeah.
Okay, sir.
Here you cannot see it, so it could not be possible that this is 1,4 disubstituted one.
Okay, sir.
So how many different number of carbons could be possible?
Six.
Sorry. So there is a symmetry over here. So you just count. Okay, so I will write this ET as OCH to CH3. Then it will be possible.
6 different carbon.
7.
6.
6. Okay, let's see. So this is 1. Okay, so this is 1. This is 2. This carbon is 3. This is 4. This is 5. And this is 6. And this side is also equivalent, so I don't need to count that. So you have 6 carbons over here, for which you need to identify the positions of the peaks. Now you see where are the peak positions. You first say check in the proton decoupled spectrum, is there 6 lines, is distinct lines? Yeah, this is 1, 2, 3, 4, 5, and 6. Yes, so 6 distinct lines are there, which is also supporting that we have predicted the correct compound. Now you need to identify which line corresponds to which one. So this is 169. This is, I'm writing 169. So this is how much it is? 132 kind of thing. 132, 130, and 129 goes by. And also 2 peaks at 60 and 15. 60, 15. So you need to assign which carbon corresponds to which peak. So 169 one.
Carbonyl.
And that means 3, right? This carbon, right? Carbon 3, I have named it 1 to 6. You just need to tell me which one. 169 is nothing but 3. 132?
5.
132 is 5.
4.
4. 4 is nearby to carbonyl, so it will be more difficult. So 4 will be here. 130? 131?
5.
5. As you go far away from this carbonyl, your desilting will decrease and your this delta value will get decreased. Okay. So here 130, this 129 will be this one 6, and the ethyl one, if the CH2 will show 60. Sorry, this is 2, and this 15 one will be shown by the 1. You have seen this ethyl one in the previous case also. So we have also matched the carbon 13 spectrum. So this is the correct structure of the compound. Okay, this 2 COET and this is benzene ring. Yes, which was
Sir, I have a doubt.
Sure.
Sir, if we consider the minus I effect of carbonyl, then there should be a positive charge on the carbon number 5. It should be more desilted.
Carbon number 5.
5. Yes, sir. If you consider minus I effect of carbonyl resonance,
Yes.
then there will be a positive charge on carbon number 5.
Yes, that is true. but since it is attached to this one, okay, so this carbon, yes, what you are saying is correct. In case of nucleophilic addition, nucleophilic substitution, this kind of thing, there is a high possibility that this will create a delta plus charge. It's correct. But here in this case, when you have two CO2 groups attached to a carbon, so here this carbon will be much more dissipated and they will have very much minimal shift. You will see this will be 132, this is 130 and this is 129, because the effect will be equally distributed among all these. Okay.
Sir, so we can say that here minus I effect, that is inductive effect, which are being considered more dominantly.
Yes, yes.
Okay, sir. Thank you.
Sir, can we match with proton NMR also, sir?
Yeah, I have solved this proton NMR. Yes. So in proton NMR, what do you see? This is a quartet, this is a triplet, and this is a multiplet. So all these things I have explained here, this should be quartet, this should be triplet, and these four hydrogens, they will give doublet or doublet, and then they will do meta coupling and they will give you this multiplet kind of pattern.
Okay, sir.
Okay. Now you need to find the next question here. That you need to deduce the structure of the organic compound from the given spectroscopic data, considering IR in mass, 1H and 13 CLMR, and UV also is given here. Okay, you first you don't need to look at the UV. First, information on this molecular formula is given, and you have to derive, sorry, not given, you have to derive it from the spectral data. So can anybody predict, seeing the mass spectra, what kind of molecule it could be? Seeing the mass spectra, yes,
Presence of chlorine.
chlorine. Okay. Anybody else?
Two molecules of bromine, two atoms of bromine.
Correct. Two bromines. So chlorine will not be present, because if chlorine is present, you will see a ratio of peaks of 3:1. Twice, so that means the peak M is to M plus 2, you will see it a ratio of 3:1. But if bromine is present, we expect a ratio of M is to M plus 2, which is 1:1. But here what you see, a peak of M plus 2. If M plus is 249, you see M plus 2, M plus 4. M plus 2, M plus 4. So it is, and also the ratio is 1:2:1. So it is only possible if you have two bromine. Okay. So one is possibly this one, 79. Another is this one, 179. Another 81. Another is this one is 81. This one is 79. Another is this one. Both of them are 81. Right. So 1:2, these two are equivalent, and this is 1. So 1:2:1 that you will expect to see, and you are seeing it here. So you expect that molecule is a disubstituted bromine. Okay, so the dibromo compound. So from here you get an idea that dibromo compound. How will be the molecular weight of bromine? Bromine's molecular weight 79 or 81. So for the first case, if you take, if in the mass spectrum you lost 2 bromine, how much will you lose? Will you lose 79 into 2? How much will be 8? 750, 158, right? Now if you subtract from 249, 158, you see we will left with 91. Okay? 249 minus 158, you will left with 91, this one. Right? So you can easily suspect that this peak is coming due to loss of 2 bromine atoms. Right? Now if you look at the IR spectrum, there is some indication that which kind of group could be present in the IR spectrum. So can you tell me which kind of group could be present from the just seeing the IR spectrum?
Sir, 100 for C double bond C.
C double bond C. Who is seeing which one?
Aromatic.
Which one?
Aromatic.
No, which one? This one, this one, this one, this one. Which one?
1600.
Yes, 1600 C double bond C could be possible, right? And here, this pattern tells you something or not? No, it's not telling
Primary.
anything. Which one? Okay, if you are not convinced that what is it is giving, now you see in NMR it is giving what?
NH2 group.
Exactly. Whenever you see a peak here, you whenever you have some IR spectrum and you see something like this sharp two peaks, closely peaks nearly 34,000 to 36,000, you can clearly identify that there is a possibility of NH2 group. And here you see there is an exchange with D2O, which also indicates that NH2 group is present in the molecule. Okay. Now, removing NH2, how much of mass will remain? If you remove NH2, NH2 is how much? 16. So if you remove 16 from 91, you will left with how much? 75. Okay. We will left with 75. And here from this UV, there is an absorption at 250 or 260, which actually indicates some aromatic compounds. And also, what you have got? You have got some aromatic compound. You have got NH2. You have got two probeins, right? So if you match that aromatic compound, okay, this matching will be later. So how much with aromatic compound this NH2 is lost from this 91, right? So in compound, your compound, you have two bromine, one NH2 and an aromatic compound. If you lost two bromine, you will left with 91. If you lost NH2, you will left with how much? 75, right? Now you need to check whether this aromatic ring corresponds to 75 or not. It is corresponding to 75, yes, if it has three substitutions, right? So benzene is nothing but C6H6. So if it has a three substitution, so it will be C6H3 and it will have 75. And what could be these three substitutions? One NH2 and two bromine. This is only possible. You need a triply substituted bromine or three substituted bromine. You have one NH2, two bromine. There is a high possibility that they all are attached to the bromine, to the benzene ring. So different structures could be possible. Now coming to the question. So you have benzene, okay, you have NH2, you have two bromines, right? So whatever I am saying that it is a triply substituted aromatic compound. So I am writing one substituent at NH2 because I know one of them is NH2 and I also know that two of them is bromine. Now what positions will be that of bromine, right? That both bromines are here, or one is here, one is there. So I don't know in which position two bromines will be there. So now, in which position bromines will be there, this will be dictated by this NMR 13 carbon and proton NMR. Okay. So in this case, you see there is a triplet pattern, right? Triplet. How many hydrogen? If you don't know how many hydrogen, if you just calculate that 6.5. And also you see aromatic region protons are there, so it is also confirming that aromatic compound is present. And the pattern, what kind of pattern you look like? First, this one is for NH2. This is 6.5 triplet. And what is the another pattern? This is nothing but a doublet kind of thing. Okay, 1:1 kind of intensity. So whatever you see here, this is nothing but 7.3 kind of thing. Okay, so one is at triplet 6.5, another is at a doublet 7.3, another is NH2, right? Anything else you cannot see here. So from this idea, you can tell that how many different kinds of proton could be possible in the molecule. You see here, two different types of proton are possible in this molecule, right? So the arrangement of two bromines, listen to me carefully, the two bromines will be like that. You will left with two different hydrogens, right? Whatever is this is a very basic idea. The different number of the number of different hydrogens you have in the molecule, the number of different signals you will get in the NMR spectrum. You will see two different spectra, two different cases. That is, you are getting two different peak positions for hydrogen. So the two bromines will be oriented such that will be oriented such that you will left with two different kinds of hydrogen. So can anybody tell me that with respect to NH2, what should be the orientation of these two bromines such that I will get with two different hydrogen only?
Ortho position.
Both ortho?
Yes.
This means this one, and this one is another bromine is this side or this side?
Ortho side.
Ortho to NH2?
Yes.
Anybody else?
Sir, meta.
Good. Meta? Both meta?
Yes, sir.
Okay. Anything else?
The two bromines should come as ortho position to amino group.
This one you are saying, right?
Yes.
Yes. Okay. Anybody else? Any other answer other than this? See, you just need two different hydrogens. Okay. Fine. So these are two are the main possible structure because here two hydrogens are there. This is suppose A, this is A, this is B. So this is symmetric. Similarly, here also two types of hydrogen is there. This is A and this is B. Now, in the NMR spectrum, you see a triplet and a doublet. So can you tell me which could be possible? So I name it 1 and someone name it 2. Which one is possible? So if this is possible, what you will expect? Your delta of A, if you see this A position, your delta of A will be, there is another hydrogen only, so it will be doublet. And delta of B, what will be this? Two equivalent hydrogens, so 2 plus 1, 3, this will be triplet. This is matching with this one, right? A triplet and a doublet. Now if I could guess this one, for delta of A here, suppose I am naming it A prime and it is B prime. Okay. So delta of A prime, what should be the pattern? It is no hydrogen, so it will be singlet. And delta of B prime, it will be again singlet. So you expect singlet. But if they are ortho to each other, both ortho to NH2, you expect a doublet and a triplet. That is what you are seeing here. So this is the most possible structure. You got this? So this is the most possible structure, that 2,6-dibromo-aniline. Now you need to confirm the structure using carbon 13 NMR. So I am writing the structure here. So how many different carbons will be there? How many different carbons will be there?
4, sir.
4. Yes. This is 1, 2, 3, 4. Now in carbon 13 spectra, you see how many peaks you have got. 1, 2, 3, and there is a very minute peak over here. This is 4. Okay. So the small peak at 140, 141, like, okay, 141. So 141, you got one peak. You got a peak at 130. You got a peak at 120. You got a peak at 109 or 110, like that. So I have 4 carbons. So which one will be of 141?
Carbon 2.
2, 1. Which is more electronegative, nitrogen or bromine?
Nitrogen.
Nitrogen, right? So this carbon will be more distillate compared to these 2 carbons. It will be 141, right?
Carbon 1.
Yeah. Now, as we go for this NH2, if we go to this one, to this one, to this one, you will see that the value will getting decreasing, right? In the previous case, that it will be highly distillate, and as I have told you that if you go far away from these groups, this value will get decreased, right? So 130, 120, 109, you expect these 2, 3, and 4. But one thing you see here, that these two has bromine atom. It is somewhat electronegative, right? Other 2 don't have any kind of atoms which is attached to this, but 2 has bromine atoms which is slightly electronegative, right? So what will happen? Since bromine is slightly electronegative, so, and also here NH2 group which has also this effect, so this one will be very much shielded. Okay. So here it will pull electron density. Since there will be a deficiency of electron density here, it will pull much more electron density to these 2 ortho positions. So since electron density will increase in these 2 ortho positions, but there is nothing in the para position which could withdraw electron density, so more electron density will be here. Since more electron density will be here, hence this will be much more shielded, and this will come at low value. It will come at this one will be of 2. And the remaining 2 1, this one will be 3, and this one will be 4. Okay. You just main thing is not to identify which kind of hydrogen, which kind of carbon is which one. You need to just carbon 13 to see. I have 4 different kind of carbon. I need to match that whether there are 4 peaks in the picture or not. This is the main motto. Then you will then assigning comes in. First, you need to check that 4 different peaks are there. So I have 4 different peaks. Okay. So this is the compound. Okay. Fine. Going to the next problem. So you need to assign the structure. Here all data are given like the previous one. And here the molecular formula is also given, C10H16O4, C10H16O4, right? So in IR you see a peak at 1725 centimeter inverse. And here it is about 3000, right? So first you need to find out dBE, 10 minus 16 by 2 plus 1 to 11, 8, 3, right? 11 minus 8, this is 3. 3 means there is a very less chance that it is a benzene kind of system. Okay. So the main thing you get here that benzene kind of system could not be present, because in benzene kind of system you have seen that there should be more than 4, 5, 6 kind of GB, then there should be benzene kind of thing. So now I am coming to this one. Okay, so this one is connecting to sp2 carbon hydrogen, whatever I have shown you the previous case. So here and 1725, which one is this should be? This should be which one?
Sir, saturated ester might be.
Ester. The previous case also you have seen this is ester. Okay. So we first assume this is ester, then we will see if this is matching with the other picture or other signatures or not. So whatever you have got, this is nothing but ester kind of thing. Another is sp2 carbon hydrogen. Now you see here mass spectrum. You have M by Z at mass spectrum. You have M by Z at 200 molecular and peak, right? You have another peak at 155, which is loss of how much? 45. From there you see a main peak at 99. Okay, I am interested in the high intensity peak, which is at 99, a loss of 11 more, sorry, 56 more. Yeah. So there is some group which has lost as a 45 mass unit loss, for which you have got a peak at 155, and from there one hydrogen is lost, you have got a peak at 154, and the 99 loss you have due to the loss of 56 more mass unit, right? Now what is possible, that you knew that OET group, if you lose OET group, you will lose 45 mass unit. So there is a high chance that you have, since you have proved same kinds of ester kind of thing, and also you have seen that the loss of 45 is happening in the mass spectrum, there is a possibility, the first thing comes to your mind, that there is a possibility of OET group. Now how to confirm OET is present? You need to do NMR. In NMR you see there is a quartet 4.1, there is a triplet 1.3. So it clearly indicates that OET group is present, right? OCH2 CH3 group is present in your molecule. Okay. Now coming to the next point. So you have seen a loss of 45 here. Now you have seen to prove that a loss of 56. So you can, I guess from somewhere that if you lose OET, you lose 45, and if ester functionality is present, which is nothing but CO OET, so if you lose OET, you will left with CO. And how much is CO? CO is 28 mass unit, right? So from after losing 45, that is OET, if you lose CO, you will lose 28 mass unit, right? But where you are losing? You are losing 56 mass unit. That means you are losing this one along with something, or maybe another group which has a mass of 56, right? Now you see that how it is possible. So one thing you can see here, that at 2.0 there is a singlet. 2:0, not, this is not 2:0, this is 2.0, there is a singlet, right? And if you calculate, if you have the spectra, if you calculate, its intensity is very high, very high intensity. Okay, And also you see, so all the remaining hydrogens is of the same quality, because if there is a different hydrogen, you will expect a different peak, but you are not seeing any different peak. So if you have CO2 kind of thing, CO2 kind of thing, which is nothing but what will be the mass? C3H5O2, and you have C10H16O4, C10H16O4. Now this pattern at 2 singlet at 2, which is nothing but the hydrogen of sp3 carbon. This is attached to any kind of group for which this is highly distillate, right? In any kind of group you cannot get this high intense peak. So if you count, you will see that it will only give 6 hydrogen intensity. Okay, so 6 hydrogen intensity at 2.0 is nothing but presence of this kind of group. But if it is attached to any normal carbon, that is a saturated carbon like this one, okay, so then this would not be come at 2. So this is highly possible that this is attached to some kind of group like this, C double bond C. Okay, and if this is possible, then you will see that this is a 6 hydrogen pattern. This will be singlet, and also count all this. So this will be C3, this part, okay, C3H6, C3H6, yeah. So add with this one, so this will give C336, C6, C6, H11, O2, and what will be your formula? C10, H16O4. So you are left with C4, H5, O2, right? And in NMR, you 1H NMR, you can see no other patterns. You see this CH10, you have 2 oxygen, you need to utilize this. So if I just subtract 1 carbon from here, making it 3, you can expect that this is nothing but CO2 So where I have taken 1 carbon. So how it will go? So if it is possible that this is present like this is only the possible way that you satisfy the structure. Okay. So a carbon double bond carbon is possible with these 4 substituents. You can see CO2 will be there and 2 CH3 will be there. Okay. Now if you can calculate, if you now can argue that why these 2 are in the same side, why these 2 are in the same side. Okay, so this idea you can get idea, and you can then solve the questions if you just write all the other possible structures and you then count how many different number of carbon is possible, or how many different number of carbon is present in the molecule, and they will then match with the peaks that is obtained here. Here you see 1, 2, 3, 4, 5, 6. 6 different carbons are present. Now I count here. So here air is a symmetry. Now if you go here 1, 2, 3, 4, and for ET 2 carbon, so this will be 6. So 6 different carbons. Okay. Now you need to match all the other peak positions. So I like to write C double bond C H3 E double bond O H2 H3. Now you see this carbon pattern. So for CH2 CH3 we expect a peak at 60 and 15. You see here a peak at 15, 60 and another peak at 15. So also you see here another peak. This is also presence of methyl, but this is more desilted, which is more possible due to this methyl, right? This methyl carbon. Also, another way to confirm that this is methyl carbon is this one. Since it has three hydrogen, so it will couple with 3, so it will give 3 plus 1 4, that is quartet pattern. You see here, this will show quartet pattern, right? So this is possible that this is that carbon. Now you have to possibly figure which carbon is this one, what is this one, and what is this one. So you left with 3 carbons. One is at if I name it, okay, I name it 1. So it's another marker. So I name it 1. Okay, name it 2, 3, 4, 5, 6. So this one is corresponding to 1. You have seen in the previous questions also. So this is nothing but how much it is? This is 2. This is the 6th one. Now 3 will be this one. Right? You have seen this carbonyl carbon is highly desilted. So 3 is this one. Now among 4 and 5, which one is 4 and which one is 5? Who can tell me? Which one is 4 and which one is 5?
Sir, 5 should be more desilted
Why?
due to resonance with the carbonyl.
Yes. So it will be this one.
Sir, I can't see the data value.
Okay, it is 155, and this is 125 or 126.
Yes,
So
sir.
5
Then
will
fifth carbon will be 150, 135.
155. Yeah,
Yes, sir, 155.
and this will be fourth one because it is an alpha beta unsaturated compound. So this double bond will be in conjugation with this one, and it will be have a delta positive charge here. So this will more desiltate, and this will have higher delta value. So you have assigned all the peaks, and whatever structure we have predicted from this sorts of data, this is actually matching what we have predicted from here. Okay, so this is the compound which is drawn over here. Okay. Okay. Coming to the next question, last question for today. So you have to you have given again the data C9H8O. Okay. This kind of structure you are given. So first of all, you need to find double bond equivalence. Six, high possibility of aromatic compound. 250 peaks is also here. So there you from not looking at this one, you can see just looking at this. This is a high possibility of aromatic compound. Now you see a peak at 1680 centimeter inverse. So in IR you see a peak at 1680 centimeter inverse. Okay, and also a peak at 1630 centimeter inverse. So what are the possible groups which could be present here?
An alkene,
Which one is alkene? 1630?
aliphatic alkene, C double bond C.
And this one?
Carbonyl absorption.
Carbon. Okay. So such kind of questions, if you are given such kind of questions, you just first see IR spectra, you expect carbonyl. Now you see in mass spectra in NMR other two NMR spectrum that from which you predict which kind of carbonyl it is. Now see here, a peak at 9 point something, 9.7, 9.8, delta 9.8. Okay. So which kind of carbonyl could be present at 9.8?
Aldehyde.
Aldehyde, exactly. So this is an aldehyde functionality which is present in the molecule. First thing you have got that which kind of carbonyl is here, and also you have got a carbon double bond carbon is present in the molecule. Now coming to the mass spectrum, MS. So here you see a mass of 132 molecular mass. You see one fragment at 103. Sorry, 132 and 131. Okay. So I have peak at 132, 131, and then 103. Okay. So how much I have lost? I have lost 29. Then another peak is at 77. So how much is lost from here to here? 26. So from here, this is difficult for you to identify which kind of fragments it will undergo to get this kind of pattern, right? So from IR and mass, I am not able to understand which kind of pattern is giving this kind of results. So I need to refer to NMR. Okay.
Sir,
Yes.
the loss of 29, we can assume that at first the aldehydic proton is removed for 1 mass unit loss, and then the carbonyl for 28.
Yes, that is highly possible. Let's see.
Yes, sir.
Okay,
Yes, sir.
so first you need to arrive at this structure and then you fragment and just match with the mass spectrum. Sorry. So you see in the NMR, the region between 7 to 8 is already there. And here, what you observed? You observed a 6 hydrogen pattern like this. So this will, sorry, this will be 5 hydrogen. So 5 hydrogen pattern will be present here. And here you will be 1 hydrogen, but it will be doublet of doublet. Right? This is nothing but doublet of doublet. It is another 1H. This is also doublet. Right? Now, what is possible that, so you got then that some aromatic compound is there. And also,
Sorry to interrupt you, sir.
yes.
You have corrected as 6 hydrogen as 5 hydrogen here in this aromatic region. But this particular module was been given by professor, but he says there is something different from this part.
Something different means?
He has said that there is alkene proton is merging with the protonic resonance with this aromatic group. That is what he has given in the lecture.
That is also possible.
What to write in this case? Whether to write a 6 proton or 5 proton here?
You need to write, you don't need to write that one. Okay, so from here you need to assign that which kind of peaks could be possible. So here from you will see that 5 hydrogens. Here it is, you can see another hydrogen that is also possible. So you just assign that this hydrogen is for this one, this hydrogen for this one. Okay.
Okay.
Okay. So here, so 5 hydrogen pattern, what I am actually involved, 5 hydrogen pattern is only possible if it is a monosubstituted compound, right? Very highly possible it is a monosubstituted compound. There is some substitution which I don't know. I have benzene, so C6H5 is there. Another group is here, which is CHO. Okay, so how much is it? CHO. So see how much I am left with. So I have C7H6O. C9H8O is the structure even. So you see I have left with C2H2 only. Right? Do I have calculated correctly? 6, 7, 8, 6, 4. Yeah. So C2H2 kind of pattern is already left here. So if there is a triple bond, I should have seen their presence in the IS spectra, but I have not seen in that presence in the IS spectra. So triple bond cannot be present. Instead, you can see that CH2 is also possibly this one, where these two are other two substituents. This is also CH2, right? So in benzene, since only one substituent is there, so yeah. So from here, there is some CH2 kind of thing. So hydrogen is there, another is this one. Sorry. Why I'm writing this way, you will get to know that. If you write in the opposite way, you will see that you match these carbon peaks, carbon positions, you will see different one. Okay. And also this hydrogen's intensity, you can match it, and you can match it with this one. So this hydrogen's coupling constant, if it is not possible to match here also, if but in the normal actual NMR spectrum, you will be able to match the coupling constant. From here you can also confirm, but for now, if you see that if there is a different orientation, the number of carbons will be different, you will see a different pattern. Okay. So here, this is the most possible structure which is present. Now you come to the mass spectrum. So I'm writing this structure. So here there is a double bond, another is C double bond of H. Okay. Sorry. Now you see this aldehydic hydrogen, this will be doublet. Okay. This aldehydic hydrogen. So this aldehydic hydrogen, this will be coupled with this one, this will show as doublet. Okay. Now this hydrogen, this has a coupling with this one, this hydrogen. Okay. Also it has a coupling chance with this hydrogen. Okay. So doublet of doublet is also present here, and also 5 hydrogen pattern, it is also possible that it is coupling with these ones. So this aromatic region, you will see peaks in from 7 to 8, also 2 1 doublet of doublet and another aldehydic proton. Okay. Now coming to the mass spectra to match this. So there is a mass loss, whatever you said, that if hydrogen is lost here, there is a chance for aldehyde to first remove this hydrogen. So hydrogen will be lost, you will get a peak at 131. So you are getting a peak at 131. So losing of aldehyde will give you this one. Right? So there is a high chance that after this CO will be removed. Okay? CO will be get removed. So you will lost 1 and then 28. So there is a 29 loss which you can find here. Okay. Next step will be like that. Since CO is removed, there is a positive charge. So what will happen? This bond will break to give a molecule of acetylene. Okay. Since this will break, so it will break to give you a molecule of acetylene. So this has mass of 26. So what you are left with? You will left with this one. C6H5 plus. This has a mass of 77. So you have got this one also. So this is a high chance that this is the correct structure of the molecule. Now I need to match it with the 13 carbon NMR. Okay. So 13 carbon, you see here that In the 13 carbon, so in this carbon, how many different carbons will be there? In this structure, how many different number of carbons will be here?
7, sir.
7. This one is 1. This is 2. This is 3. This is 4. And these 4 carbons will be same. One for this carbon. 2. This is third. Okay. So this is fourth, fifth, sixth, seventh. Okay. Now you cannot predict here. It is very much drowsy kind of thing. So you see 7 carbon pattern will be here. Okay. So this carbon, since only one substitution will be present, so these 3 carbons will be very close by. Okay. And this carbonyl carbon will be highly shielded. This will come at 193. This is 193. One will be at 152. Another I have the data of 132 and a 130 kind of thing. Okay, so in this region there are multiple peaks. So 193 could be due to presence of this aldehyde carbon. So 152. So these regions you have seen, this aromatic carbon region, they generally come at 130 to 135, right? So this carbon, so a high possibility that 152 could be this carbon or this carbon, 2 or 3. So which one will be 152? 2 or 3? Which one will be of 152? Just like the previous case, this is like alpha beta unsaturated compound. So which one will be more distilled, 2 or 3?
3, sir.
3. So 3 will be 152. And all the other peaks you will find in this region. Okay, so there will be a messy kind of thing. So actually this is the structure. What you have observed. Okay. So this is the structure of the compound that is using this data. Fine.
Sir, I have a doubt.
Yes.
How did you confirm that this is the right structure? I mean, in the alkene, this is a trans type of alkene or E alkene.
Yes, right.
Why it can't be the Z alkene?
Yes, it could be Z alkene, but then you need to calculate how much carbon signals will be there. Okay, and also if you have these data from here, you can calculate this coupling constant. Coupling constant will be different. Okay.
Okay, sir. Thank you.
Okay.
Is it possible to calculate the J value from this spectrum? What is been given in the question, sir?
No, that is not possible because this is too messy. But if it is plotted using some software like Nova, so from there you can easily calculate. Okay.
But generally, we can say it is only cinemaldehyde like that.
Yeah, cinemaldehyde kind of thing. Yeah.
We need not mention whether it is cis or trans.
If trans in case of cis, the number of carbon signals will be different, I guess. Okay.
No, how to, I'm not able to get it. How to differentiate it whether it is cis or trans based on the carbon signals?
Because if number of carbon signals you will see, it will be different. Because there will be a symmetric kind of pattern you will see. If this is a trans or cis, depending upon that.
Okay. So I have two more clarification. If you permit, I can.
Go on.
So, is there any requirement if such questions have been appeared? Whether we have to give the fragmentation pattern for all the molecules which are going to finally conclude?
Not at all.
Because the question says it is like that. It's only
Your
deducing
question is
the final.
actually, you see, your question is given that you
Only
have to draw the structure. Yes. So whenever you will draw the structure, you need to do the fragmentation. You will do it by your own. You will do the fragmentation and check that whether it is correct or not. The elucidation of the main structure is important mainly. Okay.
Okay. And can you put some highlights on the UV spectrum so it will be useful for us, at least for the only one sample, the first example, 1st problem. Can you please just give 1 or 2 minutes time for that?
UV I will explain in the next module.
No, at least 1 or 2 key points so that we can.
So UV is actually here to first 1 or 2 cases. You see here absorption at 250, which actually tells the absorption of benzene kind of thing. If you know UV, the benzene actually absorbs in this region, so it is an indication of this aromatic kind of thing. Okay. So if it is highly going to 282 or 290, it is there a possibility that CO is also present, and this is also absorbing here. Okay.
Will it be enough if you write it is an aromatic system with the carbonyl, or we need to mention whether we need to mention about what kind of transition it may go with?
You can mention if you have your idea that what kind of condition it is, you can easily mention.
If it is carbonyl, then I can say it is N to pi star.
Yes. Yes.
And pi to pi star for the aromatic system.
Aromatic system. Yeah.
Okay. Sir. Okay. Thank you.
Okay. So all the answers I have written here. Okay. So the 5 answers that the possible is I have written here. So there is a question that I would like to give you. You try it yourself. I will solve in the next class, where this is the structure of the molecule. C4H8O. So this has a molecular ion peak at 72 and another peak at 43. Okay. In NMR, it is showing a quartet and also a triplet. A quartet is at almost, you can say it's 2.5 like a thing. This is quartet. Okay. And also from here you can get a triplet of 1.1. Okay. And in a IR, you will see there is an intense peak here and also an intense peak here. Whatever possible group could be present in this molecule is clearly given from this IR spectra that I have discussed today. You have this mass spectra and you have also the NMR spectra. You try it yourself, what kind of molecule it is possible. I will start with solving this question in the next module. Okay. You can take this. So you can take the screenshot, or I will see at the slides also. So there, from there you can get it. Okay. Okay. Yes, KMCH pharmacy, you have find it out?
Yeah. Actually, I just wanted to know the evaluation of my assignment, because what was the mark allotted, which I wanted to know. I have sent a mail also to the NPTEL team. I didn't get any response from them. I have sent 2-3 mails. What is the breakup of each question, the marks that has been awarded?
For this type of question, this is 25 marks exam, so it will 5 marks will carry for each question.
No, the marks that has been awarded to the assignment which I have submitted.
Okay, so we are not we TS are not actually checking the assignment.
I'm just seeking a person whom I have to, because I have sent mail and there is no response.
You have to mail them also. Okay.
So 2-3 mail I have sent. I don't know. So that's the reason I'm just.
So you keep sending them reminder mail, or you have sent how many mails?
2 mails I have given in this regard.
Okay, so whenever
They have mentioned it should be, since it is been corrected by TA, you have to ask only TA because it is done manually.
Mhm.
They are asking the only TA to be answered. I don't know which TA to whom I have to ask.
So I am not actually taking any kind of assignments. Okay, so my work is to solve this assignment.
Uh, I'm sorry that I'm asking you, but is there any possibility which I can communicate to somebody else who can I get?
I don't think so. This is the only way that I have told you, that directly mail them.
No, I'm mailing it and
I understand. I completely understand. But this is the way that we actually get connected to them. So this is only the way. I don't have any other idea, any other way. So you
Okay.
keep mailing them.
I'll again make a reminder what to do.
Yeah. You just make a reminder. And
Yeah.
whenever you get the mail of any live session, you get a mail, right?
Yeah, I'm getting mail for that.
You would you write in their reply mail also that I have mailed you. You can do that also. Okay,
Fine, thank you.
that will be helpful, I guess.
Thank you.
Okay. Okay, so the session is over for now. So we'll meet in the next session. It is the last session for this course. Where I will talk about the UV. Okay. Okay, Lawali, you are asking, please, how will I be able to be added to a WhatsApp group? First of all, I am not actually in the group. Okay, so I think the group is created by Tushar. So in the next session, when you will take this, you join on. He probably takes it on. If I am not wrong, it's on Friday. He takes it. So you join and he will send you the link. Okay.
Okay, sir. Okay.
Sir, can you upload this link, sir?
Which link?
Today's recording, sir.
Yeah, it will be shared in the YouTube, and also you will be provided the link.
Uh,
Yes, it will be provided.
Tomorrow is last date for assignment. So,
Oh, okay. I will upload it today. Okay.
uh,
Today is not possible. It's already night. So maybe tomorrow morning it will be uploaded.
thank you, sir.
Okay. Is there any WhatsApp group? Yes, Prakash. I think Tushar has created a WhatsApp group. Maybe. Okay. So
WhatsApp.
yes. And the other TA Tushar, he has probably created a WhatsApp group. I'm actually not there, so you just talk to him.
Sir.
Okay. Okay, so I am logging off. Okay.
Lawal. Hello, Lawal. Navari.